Okay, so announcements for today. I opened up the chapter 22 sapling. Due date is currently set to 9 a.m. on Friday next week. Depending on whether I finish the chapter today, that may get pushed forward, but we'll see how we go. And then the exam review is coming up Sunday afternoon, 2 to 4 in Math 100, same as usual. And the exam is Tuesday night, 7 to 9 p.m. in Chem 140, also same as the last two. All right, questions about those? Alrighty, cool. So I am hoping to cover all the remaining reactions from chapter 22 today, and then maybe we'll get done with synthesis practice from the notes, maybe not. Okay, so we spent the last couple lectures looking at aldol or Claisen chemistry. So basically you make an enol or an enolate, and then you send it to go attack on another carbonyl, and you stick together two different molecules that way. So it's a great way to make carbon-carbon bonds. What we're going to look at today is another way to make carbon-carbon bonds that's not quite the same but similar. It still goes through the enolate. So alkylation of ester enolates. Okay. So this actually traditionally is done on the carbonyls that are the easiest to deprotonate. So we've seen pKa's for a few different carbonyls, but the ones with the lowest pK value, the easiest ones to deprotonate, are the ones with a carbon that's alpha to two carbonyls at once. So in between two carbonyls is the easiest spot to deprotonate. And we saw last time that that's because you can actually show three different resonance forms for that molecule instead of just the normal two for a given for an enolate. So the two that are really commonly used traditionally for doing this are this one, which is called malonic ester. Or I guess this one is technically a malonic ester. So malonic acid is this, but without the ethyl groups at both ends. It's just like two carboxylic acids. This one happens to be the diethyl malonic ester, I guess. But you can do it with whatever alkyl group on either end because it's not going to be there in the long run anyway. Or you can do it with this thing. So similar, only instead of an ETO group out on one end, it's got a methyl group. So this one is called an acetoacetic ester. And this one is technically ethyl acetoacetic ester because it's got the ethyl group on it. Okay, so the important part is both of them have this same carbon in the middle that if you deprotonate it, you're going to have three different places to put that negative charge. You could put it on the carbon, which is the least sort of stable out of the three options, or you could bump it up to the left oxygen or onto the right oxygen. Okay, so we're going to start putting this in a base, and just like we did for Claisen and Dieckmann, we're going to use the same base that matches the ester part of the molecule so that we don't accidentally do a transesterification. So we're going to take this thing, we're going to hit it with ethoxide. Going to make the enolate. Based on what we know of pKa's, so the pK of this thing in the mid-teens, about 16-ish. pK of this thing is probably about like 10 to 12-ish, depending on, I don't know for this exact molecule, but for this kind of doubly alpha carbon, it's usually in that range. Okay, so this is actually real easy to deprotonate, and in fact, even though this is in an equilibrium acid-base kind of thing, it's actually favoring making the enolate because this is more stable than the base that we're making it from. So I guess you could, if you wanted to, show this as an equilibrium. So basically, you add one equivalent of ethoxide, and you're actually getting the majority of the molecules quantitatively converted to the enolate, which means that then you can add, as step 2, some kind of alkyl halide. So let's say we're adding, just to match the one I put in the notes, this alkyl halide. This can kick down, and rather than going out and attacking on a bromine atom or a proton or another carbonyl molecule, now we can just do good old-fashioned SN2 onto that thing. So we're using our enolate to do the job of a nucleophile. It's a little bit more complicated than a nucleophile that we saw in like the alkyl halide chapter, but it's still doing pretty much the same thing as far as this alkyl halide is concerned. So we end up with this, and now we've got carbons 1 and then this branching group. So we end up sticking that new 4-carbon chunk onto the middle carbon here. Okay. So there's no need to like lock in the product or anything like we did for Claisen because the equilibrium is sort of on our side already. But if we want, we can actually do a second round of this. So we can hit this with ETO minus again. Deprotonate, make the enolate. And then bring in a different SN2 capable alkyl halide. I don't know, maybe benzyl. So like this. Take down, go attack. And then you could have a second R group attached off that carbon. Okay. So that's pretty in line with what we've seen other stuff doing in this chapter. We're just attacking something that's a little bit less complicated than when we went after a carbonyl.
Do sterics become an issue in this case, kind of for adding those different alkyl groups?
Good question. I think it seems to work okay. Like I haven't seen any cases where sticking a big R group on here slows it down enough to be no reaction. I guess like the biggest issue is sterics around the thing that's actually getting SN2 done on it, like always. I guess like if you had some huge group on there, it might start affecting it. But yeah, we can probably assume that it's going to be safe to go unless like things are getting really ridiculous. So yeah.
Is the carbonyl on the ester just more reactive than the carbonyl on the other side, or is that?
I could have shown it going either way. I am just doing it that way because that matches how I showed it in the notes. Yeah. Yeah, and really, like I could also draw like the equilibrium brackets and just show it equilibrating between all three. But yeah, however you show it is totally fine. It's all the same thing. So. Okay. Or I could have shown it with a minus charge on the carbon too, which is technically correct, just the minor resonance form too. So, okay. So once we stick on one or two R groups of our choice onto the central carbon, getting to this point looks pretty much like everything else in this chapter. The interesting thing is what we would normally do next to this, because we can actually take this molecule and start going through some chemistry from a couple chapters back. So what we're going to do at this point is we're going to hydrolyze that ester to a carboxylic acid. And then for both of these molecules, you'll notice that once I turn those esters back into the acids, I've got something that looks like a great candidate for decarboxylation, because in both cases I have a carboxylic acid that's 2 away from another carbonyl. So, I'm going to hit this with, and usually this is done in base first, just because it's a little bit easier. So NaOH and H2O. I'm just going to abbreviate these as R and R prime because the exact identity doesn't really matter. So we hydrolyze it to the carboxylate. Then we do a water workup. Get it to here. And then if we heat it, or if we're heating it the whole time we're doing these two steps, which we usually are, then this entire group is going to drop off and we're going to be left with just an H in its place. So like that. Okay. So overall what we've accomplished is we end up with this, basically a molecule of acetone. But with two possibly different R groups of our choice stuck to the same carbon on one end of acetone. Okay, so you might be asking, like, why did I bother using such a big molecule to begin with? Why didn't I just start with acetone and deprotonate that? That's because this is kind of older chemistry when we didn't have LDA. And so the only easy way to deprotonate reliably was to have the H's be alpha to 2 carbonyls, so it's a lot easier to pull them off. And then you can go do SN2 more easily. And then later on, you can lop off half of the molecule when you're done sort of using it to make things easier. Uh-huh.
What about the methyl hydrogens? If you were to add an excess,
Mm-hmm.
would those also be alkylated as well?
These ones here?
Well, yeah, more like up there, like on earlier stuff.
So the problem is the pKa's of these ones are like up around 20-ish, and so they're just not like you would get some deprotonation like a little bit of the time, but they're just not as favorable as the ones in the middle. So yeah, good question though. Like that is like something to be aware of, but it's just so unlikely compared to what's available that it's going to be super minor. Okay, cool. So overall, when I'm doing this reaction onto acetoacetic ester, this is actually called the acetoacetic ester synthesis. Okay, so we just start out with this molecule. I guess I didn't actually combine all of it into one thing in the notes, but just to put it all together in one place. Okay, so you can alkylate once, and then if you want, you can alkylate twice with the same or a different R group. And then we can actually usually like lump these last few steps into the same arrow. We just do step 1 and step 2. So usually it's going to be like NaOH and H2O. And then step 2 is just H3O plus and heat. and that gives you this molecule, so like acetone with 1 or 2 R groups attached to the same carbon. Okay, question? So good question, like, because, we've seen acid hydrolysis as well. It's usually done in base, and I don't know if there's any particular good reason for that. I think it might just be, like, historically that's the way it was done. It might also be it's a little bit easier for base catalyzed hydrolysis. Maybe it's faster or something, I'm not sure, yeah. So, but yeah, I think, like, on paper at least, we could just do acid catalyzed hydrolysis, and that would also get us the same product. So you could just do it as a step 1 is H3O plus in heat, and that should get you to the same place. Okay. So that's one of them, acetoacetic ester synthesis. Malonic ester synthesis. It's pretty much, I'm not going to write out the whole thing. I'm just going to draw the starting material and where it gets you. But same steps, and you will eventually get to this, only rather than having a methyl group out on the right of the molecule, we're going to end up with a carboxylic acid out there. Okay, so you alkylate once or twice in the middle, hydrolyze both esters now, and then decarboxylate, and you're left with basically acetic acid with 1 or 2 R groups of your choice on there. Okay. So questions? Yeah.
So for all of these, be it the malonic acid or the acetic acid
Mhm.
or ester, the ethyl group on that's making the ester can be anything.
Yeah. Usually it's ethyl, I think, just because that's cheap and easy to get on there. Like, it could be pretty much anything though. So, yeah. So long as it matches the base that you're using to deprotonate in the first step. Yeah. Okay. Other questions about? Yeah. So I'm about to cover that, and it turns out it has some drawbacks that actually make this the better choice a lot of the time. Yeah. Okay. So, all right, cool. So, I guess one other thing that I should cover while I'm over here is that another way you can look at it is from the R's point of view, I'm extending the chain by either 3 carbons here or 2 carbons, or 2 carbons. So if you're looking to add a couple carbons to your chain and have it be a carboxylic acid at the end, this is a way to do it that's kind of easy. Okay, so modern equivalent is using LDA. So we could accomplish pretty much the same thing if we just do so say we take this ester, here's LDA, and we know we can make the enolate pretty easily on this thing. And then we can go attack our alkyl halide that way. And like we saw before when we were using LDA, since this deprotonates like very favorably and quantitatively, we're getting full conversion to this. So as long as we have at least one equivalent of LDA, we're not going to have to worry about this thing sort of attacking itself. And we also don't have to worry about which proton gets pulled off on the ester because there's only one location. So here we could also do whatever R group by SN2 again. And accomplish something pretty similar to the malonic ester synthesis. I guess if we want, we can do the hydrolysis step at the end too. Okay, so I'm showing this for like a single R group, but we could do it twice if we wanted. Okay. So side note on this is it turns out like not to work very well for ketone enolates. So over-alkylation turns out to be an issue. So I think that's primarily down to just the slight difference in pKa's between esters and ketones. There might be something more involved too, but I do know that trying to use LDA to alkylate ketones generally gives you a mixture of products, like some with a single R group and some with multiple R groups on there. Okay. So basically we can use LDA to like simulate doing the malonic ester synthesis pretty well, but we can't use LDA to simulate kind of doing the acetoacetic ester synthesis. So really this older school stuff actually turns out to be less problematic as far as getting the R groups on there that we want a lot of the time. Okay, question.
So why doesn't the LDA work well for that example up there?
Oh, this one up here?
Yeah.
Um,
Because with the high, like it seemed to, like it could actually alkylate the methyl. Or
right. I think. So I'm not 100% sure. It might also be that like competing like aldol on other copies of itself might be an issue because we do still have a molecule with like 2 carbonyls in it. So yeah, good question. So I'll have to get back to you on that. Sorry, yeah. Okay. So other questions on that? Okay, cool. All right, so the last category of stuff that we're going to look at is related to carbonyl additions, but with an extra twist. Okay, so we're going to look at conjugate additions. Okay, so this whole section is about molecules where you have a carbonyl conjugated to an alkene. Because it turns out, so we already know from like chapters and chapters of looking at this that we have a delta positive on the carbon of the base of the carbonyl, right? Because this carbon is attached to something more electronegative. So you can actually show a resonance form where you have a negative charge on oxygen and a positive on carbon. If you want, we can actually draw that out because that might make this next part easier to see. Okay, so this is minor, but affects reactivity. So the carbon definitely acts like it has some portion of a positive charge there. So when we were just looking at a regular carbonyl, that was pretty much all we had to worry about. But once we're conjugated into an alkene here, we can actually show other resonance forms where the alkene itself gets involved, because we have, once we show it doing this, we have this whole 3-atom subunit going on, 2 atoms double bonded, one with a positive charge. We can actually move that around. To get it out to here. And these are looking increasingly unlikely, but there's still like some charge distribution out there. So even more minor, but still, as it turns out, significant enough to where not only do we have a delta positive on this carbon, we also have a delta positive out on there. Okay, so what this means is that if this guy is just sitting around and a nucleophile comes in, the nucleophile could actually go for either of those 2 carbons with the delta positive. So we've spent several chapters now looking at nucleophile goes straight in for the base of the carbonyl, kicks that up, and exactly what you'd expect. You end up with a nucleophile there. But we could also have nucleophile attacking here on this partially positive carbon, which means that now we're going to pretty much just kick the electrons around. We could show them dumping onto this carbon, but what's more likely, because that would give us basically like an enolate-like thing where we'd show the negative charge on carbon. So it's more likely, or the more dominant resonance form, is just kicking those electrons out to the oxygen. So you end up with this going on. And then once we add H, coordinate there. We can either have exactly what you'd expect for regular attack on a carbonyl, or like this. And you might be wondering, why don't I just stick the H straight on the O minus? I could show that happening, but then I'd have an enol, which would just rearrange itself immediately anyway. So may as well just save myself the trouble and show it going straight to the final ketone form, or aldehyde in this case. Okay, so these 2 things, if you look at it, the nucleophile has the option of attacking either of 2 positions. And if we look at the proton as something that also got added to the molecule, this is sort of a 1,2 type of addition, just like the 1,2 alkene additions we saw before. Or direct attack. Or direct addition. And these are the 1,4 addition. So this is conjugated attack. But when it's happening to a conjugated carbonyl like this, it gets another name attached to it, and this is called Michael addition. Okay, so Michael addition is just 1,4 conjugated attack on a carbonyl specifically. Okay. So questions about that so far? Okay, cool. So you might be wondering, how do we know which one of these is going to happen? Turns out it depends a lot on the identity of the nucleophile. Most nucleophiles, if they're given the choice between these two options, they have a preference for one over the other. So ones that favor 1,2 addition are alkyl lithiums and lithium aluminum hydride. Ones that favor 1,4 addition are going to be actually a lot of nucleophiles that we saw in the alkyl halide chapter. So like CN minus, RS minus, any kind of amine. So usually like the weaker bases will tend to favor conjugate addition instead. We're not really going to get into the reasons why, but generally like, I guess these ones tend to be called like harder nucleophiles. They have sort of a smaller, more concentrated charge is how you can think of it. And they tend to go in for the bigger delta positive on the carbonyl. These ones tend to favor attacking at the smaller delta positive instead. So amines, cuprates, as it turns out, prefer 1,4. And then most enolates, or all the enolates that we're going to see, will attack 1,4 preferentially as well. Unfortunately, some nucleophiles are just going to give a mixture, and those are kind of the in-between ones. So like sodium borohydride will give a mixture of 1,2 versus 1,4 attack, and so will Grignard's. So this is about the only difference that we're going to see between Grignard's and organolithiums is if you've got a conjugated carbonyl and you want to attack at one location only, and it's 1,2 that you're after, then use the lithium. And if you want 1,4, use the cuprate. Don't use Grignard's on these things. Okay. So let's look at an example of enolates attacking. I guess technically, like I said, Michael addition up here for 1,4. Technically, Michael specifically means enolates going 1,4. I guess if you're attacking 1,4 with something else, you could call it Michael style addition. But technically, Michael, the chemist himself, like figured out this for just enolate specifically. Okay, so like, so we have some enolate here, maybe the enolate of acetoacetic ester. And we have some conjugated carbonyl, maybe this one. So the attack here is going to be just a regular enolate style attack from this thing's point of view. But the place that it goes for on this molecule is out onto the end of the conjugated chain. And then we kick those along. Okay, numbering here might be helpful just to keep track. 1, 2, 3 carbons. So I'm going to form a new bond to carbons 1, 2, 3. 3 has my O minus and an H. I now have a double bond between 2 and 3. All right, so this is a very easy and common place to lose a carbon or two by mistake, so definitely like make sure you're carefully keeping track of this. But then once I do the workup, should be getting to there. Okay. So questions about that one? Okay, awesome. All right, so the last reaction that I'm going to cover in this chapter is actually putting together a couple of ones that we've seen previously. So it's not actually a new reaction, it's just sort of combining a couple of things in sequence, but it turns out to be useful enough that it gets its own name. Okay, so this one is called Robinson emulation. In British texts, sometimes they spell it as annihilation, but this word just means forming a ring. Okay, so this thing is, you start out with two molecules. Let's call them A and B, which I'll draw up in a second. So first, A does Michael addition onto B. And then B does an aldol condensation back onto A. Okay, so that's kind of the big picture. Let's look at how that might work in practice. Okay, so I'm going to use this for A, and B has to be something that Michael addition can be done onto. So it's got to be a conjugated carbonyl. We need at least one alpha proton out on the other side of the carbonyl for reasons that will become apparent pretty soon here. So B, I'm going to use this molecule. So this, the name of this thing will often be given in like the non-IUPAC common naming system. So this one is methyl vinyl ketone. So it's kind of the bare minimum of what you need on B for this to work. You can have other groups on there too, of course, though. Okay, so we are going to hit this thing with base. So we're not using any esters here, so it doesn't actually matter too much which one we use, but we do, as it turns out, want to be at equilibrium, not like quantitative deprotonation. So let's use maybe hydroxide should be fine. Okay, so we hit this whole mess with hydroxide. The easiest H's to pull off are the ones in between the two carbonyls. So we'll take that. And then this enolate we now know is going to go do Michael addition onto here. I'm going to start numbering again. 1, 2, 3, and 4 are the atoms of that molecule that it just attacked. Okay, so 1, 2, 3, 4. Carbons 2 and 3 have a double bond between them. Carbon 3 has an O- on it. Okay, so that's where we are for now. So then to finish up the Michael addition part of this, we just want to show this getting protonated from whatever we got handy. I guess if we're doing this in OH-, we also have the conjugate acid around probably. So aqueous base. So that's that part done. That's the Michael addition steps finished. So A has finished doing Michael addition onto B. Now B, it's going to do aldol condensation back onto A. So I could deprotonate either of these alpha positions here on B, but if I want to make a ring that's like the ideal size for stability, I'm going to want to deprotonate these ones down here. So this is why the methyl group on the right end of B was necessary, or something with at least one alpha H, because I got to deprotonate there next. So make the enolate out here. And now I can go do an aldol addition onto one of the carbonyls here. So like that. And this is where the ring forming step is actually happening, because I'm closing down a ring with 6 atoms in it. So that's 2, 3, 4. If you want, I guess you could say like 5, 6, 2, 3, 4, 5, 6 becomes. Okay, so that's my new ring. Carbonyl there, O minus here, and 3 now has its carbonyl back. Okay, and then from here, we're just going to finish up aldol condensation. So I got to protonate that O minus first. So like that. And then if you remember in base, the aldol condensation step is that weird E1CB mechanism. So I'm going to take that H, make the enolate one last time. Boot that out. And there. All right, so it's a ton of steps, but if you keep track of what we're doing and why, it's actually like not anything new. It's just keeping track and making sure we're doing like the right steps for that half of the mechanism at the right time. Okay, so overall what I'm doing is I'm making this new 6-membered ring, and the disconnects are there and there. So basically, if you're working backwards, look for a new 6-membered ring. With a conjugated alkene, or an alkene that's conjugated to a carbonyl as one of the disconnects at where the ring formed. And the other disconnect should be like 1 carbon away from a different carbonyl. Okay. So questions about that? Yep.
If we're worried about the side product with OH attacking the carbonyls in this, instead of acting with the base.
Yeah, you could definitely get some attack from the OH on the carbonyl, but it wouldn't really get you anywhere permanent. You'd just be making like the diol temporarily, and then it would just kick back out eventually when it realized that there's nothing productive that way. So yeah, good question. Yeah, I guess like always be on the lookout for side mechanisms that look like stuff that we've done, but then if it turns out not to go anywhere, then we're okay. So okay, so how many minutes I got left here? Okay, so I've got a couple minutes left, so just one more kind of summing it up part from this section. So if we're trying to add R groups onto the molecule. We can actually pick and choose what adds where now just based on what we're adding. So if we want to attack directly onto the carbonyl, we can add 1,2 with alkyl lithiums. If we want to add an R group here, we can add 1,4 with a cuprate, but we got to make an alkene there first. So we could do that by doing this. We know that in acid it just halogenates at the alpha position once, so let's do H3O plus Br2. Add a bromine there, and then like an E2 elimination would give us that. And then we can do 1,4 with cuprate, the way that we want. Okay. And then if we're trying to add an R group here, we can make an enolate and go attack an alkyl halide, but depending on exactly what molecule we have, that may not work great. So you're probably, depending on, if it's this exact molecule, you might not get a great yield, but it's a way to do it. And I guess if you sort of generalize this to maybe like ester molecules or other molecules, it might be a better choice there. Okay. So I'm going to wrap it up there, and then I'll finish synthesis practice on Monday. But I'll also do a bunch of practice problems at the exam review session. So if you guys can't make it, then you can watch the lecture capture.